Thank you so much for being here and making friends with your neighbors. I'm super excited to see the packed house, and I'm really excited to be here to talk with you all about data visualization for scientific discovery. Oops. I'm Zan. I'm a data visualization designer and engineer. I'm currently part of Google's accelerated science team. My goal with that team is to use data visualization to help a team of scientists, statisticians, data scientists, and machine learning engineers analyze their data and make discoveries. So I'm just going to start by telling you everything you need to know about Data Vis. Pie charts are bad, non-zero bar charts are bad, dual axes are bad, rainbows are bad, chart chunk is bad, and a high ink to data ratio is bad. So, well, that's the end of the talk. I think I've covered everything. Any questions? These are the off-quoted rules of Data Vis. I have fairly strong opinions on all of these. Some of them I agree with somewhat, some of them I disagree with vehemently. But they remind me a lot about how we talk about food, that I don't think they're a very useful way of thinking about visualization. With food, everything is bad for you, even things that are obviously necessary, like calories, fat, and salt. And I think better to have a few good guidelines than a bunch of rules telling you what not to do. So in the case of food, I really enjoy Michael Pollan's eat food, not too much, mostly plants. And in the case of Data Vis, I would like to propose create small multiples, which are many related charts, use color intentionally, and optimize your charts for your time, energy, and attention. Maybe not quite as snappy as Michael Pollan, but I'm working on it. But before we get into those three specific topics, I want to talk about the bigger picture of that. The question of is it good or bad depends on your goals, context, and constraints. For example, with the case of food, is a candy bar good for me? Well, it depends. Am I at home drinking tea? Maybe it's not so good for me. Am I on a week-long backpacking trip in Patagonia? Maybe it's fantastic. I need that extra sugar to get me through the next couple of miles. In the case of visualization, these are two visualizations about when babies are born, based on the same underlying data. Which one is better? Well, it depends. What's the point of the visualization? How much time do I have to create it? Who is the audience? Is it made for somebody else? Is it made for me? Do I care about day of week, which I can only see in one of these? Do I care about total values or difference to mean? Even this is kind of one's more for communication, one's more for discovery. Even in a space where we're thinking only about discovery, these are two same exact data in both these plots. This is data from a sensor on the coast of California looking at wind direction and wind speed in December 2017. Which visualization is better? It really depends. I find the one on the right a little bit more intuitive because you have that sense of circularness and direction and length being speed. But there's a lot of occlusion, a lot of data that's harder to see if you really want to kind of dive in, see what data you have, what's missing, make more detailed comparisons. So it depends. And two of the major ways that we break down visualization is for communication and for scientific analysis and discovery. And within analysis and discovery, we have kind of the exploratory mode of like, oh, what if I try this? What if I try this? What if I try this? Ooh, that looks interesting. I want to learn more about that. And more of the pipeline mode, where you're getting a new batch of data, you're going to run your pipeline on it, you're going to do your analysis, and maybe, hopefully, you have some charts as part of that. And these types of things beg different fundamental questions. In communication, things like, does it attract the audience's attention? Is it true to the data and not misleading? Does it get the message across? And I think this is where a lot of our rules come from, is the communication space. Especially things like, is it immediately interpretable? Will somebody who's never seen that before be able to interpret it in 2 seconds? Which in science might be less relevant when you're looking at that same chart every single day. For analysis and discovery, I want to ask questions like these. How much time and energy? If something's important, will you see it? How long does it take? How much mental effort? How hard is it to ask a new question? Will I use this tool often? Is a learning curve okay? I especially want to point out two of these. If something in your data is important, will you notice it? In particular, for science, this is so important. You don't want to overlook that, like the nugget of discovery. And it's okay to risk something looking important that isn't, because you're going to do more analysis afterwards. You're not done at this moment. And I would much rather risk something looking important but not being, if it means I'm going to see the important thing, than miss the important thing for the sake of making sure that I never see something that might not be important. And your time and your energy is your most limited resource. In particular, this is not the number of charts. Often having more charts might actually be easier to interpret. And especially for Data Vis pipelines, where once you make the chart once, you get to have it every single time that you run the pipeline. It might be worth that initial investment if you're able to have more charts that are tuned for a specific purpose and make it easier to analyze. So just to sum up, is it good or bad really depends on your goals, context, and constraints. And that underlies everything else we're going to talk about today. Let's now dive in. This applies for food, Viz, and of course it applies for engineering, machine learning, and statistics as well. And I think in statistics we know, of course, there's no best algorithm in statistics. It depends on what you're trying to do. The same thing applies for visualization. There's no best visualization. It depends on what you're trying to do. So let's talk about those 3 topics. Number 1, creating small multiples. So what is a small multiple, or what are small multiples? Lots of small charts, similar to each other, that you look at the same time. Here's an example. 3 cities in Texas with the wind direction out of 360 degrees and the wind speed as a heat map. And why small multiples? Because you can't compare things you can't see. There's a couple different ways to think about small multiples. The canonical one is with the same form and related data. Let's say that we're interested in the relationship between wind direction and wind speed in Texas, and we have data from a few airports in Texas. We could make a single chart like this, and we can learn something from that. But I would argue that we would learn a lot more by looking at all 3 of these cities separately. Because we start to see, hey, what's common? What do we see in all of them? Like, wind coming from the south is pretty common in all of these cities. We might see that there's something funky in our data in El Paso and want to understand more why we have a little bit of a gap there. And we can start saying, hey, in Austin, sometimes the wind comes from the north, where in Houston, that's a little bit more northeast or north, maybe a little northwest. Where in El Paso, we have this bump in the west that we don't see in the others. So start being able to see similarities and differences gives us a much richer picture about Texas as a whole than just looking at Texas. And I would argue that this is actually easier to interpret than the previous slide. I would also argue that we should create small multiples where the data is actually the same in every graph and the form is different. And unfortunately, this is not really a canonical thing to do, so it isn't really built into a lot of our tools. Sometimes you have to work a little harder to get it, but hopefully we can change that going forward. So what I mean by that is, let's say that we're interested in the relationship between wind direction and temperature in Austin. So perhaps look at a chart like this, where we have temperature on the x-axis, wind direction on the y-axis. We make a scatter plot. And then we look at it and we're like, you know what, this is 3 years of data taken at 15-minute intervals. We have tons of obfuscation. I have no idea if each of those points represents a single data point or 100 data points or 1,000 data points. So I'll do the normal thing of, let's throw in some opacity to get a sense of density. This is 0.1 opacity. And I start getting to get a more robust idea of what's happening, the relationship between temperature and wind direction in Austin. But why stop there? What if I go more, and why just look at 1? What if I look at 3 versions of the data at once? The top one is full opacity, middle is 0.1, and bottom is 0.01. I'm getting different things out of these charts in a way that I think is really complementary. I don't think there's one best chart, and maybe when you're ready for publication, you'll choose the best one because you're super space constrained. But in analysis, I actually want to see all 3 of them. We can do this with histograms instead. Here's a histogram for Austin, Houston, and El Paso. So small multiples, 3 different cities that we look at the same time. We have temperature on the x-axis. We can kind of see different shapes here. Houston looks a little bit funny with those bumps. So if we'd actually looked at both the 5-degree bin width and the 1-degree bin width, it might be more robust. It might see more in our data. And you can actually see in Houston something's going on. My best guess is this is some weird conversion between Celsius numbers getting rounded and then getting converted to Fahrenheit. And there's just certain numbers that you're never going to get if you do that. And for more on bin width and histograms, there's a link here to some more documentation about the importance of varying your bin width. Resources for this, Matplotlib, there's a subplots example, Seaborn, Facet Grid, Altera Trellis. I don't know what Plotly is. I haven't gotten to use Plotly as much. Using color intentionally. Point number 2. So I'm going to talk a little bit about how we process information. The basic visual attributes are actually perceived without any conscious effort. This is called pre-attentive processing. And this is done in parallel while attentive processing is done serially, and therefore much slower. And I want to emphasize the effort here. And I'm actually using pre-attentive processing to show you the effort by coloring it yellow and making it big. And this is the part that really matters, that I was talking earlier about. We want to make things easy for ourselves. We want the important stuff to pop out at us. We want to make it easy to see the things that are important. And using pre-attentive processes can help us with that. And a lot of our canonical visualization forms are based on these pre-attentive processes. Things like line length is the reason bar charts exist and the reason why it's so important to have zeros or a meaningful baseline for a bar chart. But the thing that I want to talk about today is the pre-attentive processes that have to do with color. These are intensity and hue. And the best way to do this is with an example. So I'm wondering, do you see any interesting patterns in this set of numbers? And I can ask a more specific question. How many 7s are there? Does the answer just jump out at you? Let's try the typical default. This is what, if we have categories in our data and we throw a color on the categories, this is the type of thing that we normally get. Different colors for every category. It's easy now, right? But if this is a sequential data set, so let's throw an ascending color map on there. We might start noticing some patterns here, but it's still hard to answer our question. Veridis is super popular, so we could use that. But all I see are the 9s. Maybe we're interested in extremes. We could use a diverging color map from 4.5. And we might start noticing some interesting things in our data set here. But we still haven't answered our question, and we have a really specific question. We want to know how many 7s there are. So let's just do that. And now we can both see the 7s and where they are in this data set. Maybe we're interested in the 3s. There's lots of them. What about the 1s? Did anybody notice that it is the loneliest number? We can also use highlighting with small multiples, bringing it back to our previous point. Where now we can look at 10 charts at once with highlighting, focusing our attention on different aspects of the data in each of these charts. Or for a more general analysis, maybe with a more general question, we could look at different color schemes that emphasize different aspects of the data and maybe help us notice different things in each one. So let's bring this back to some data. So let's use color intentionally. And the way we're going to do that is we're going to make the mapping from the numeric domain to the color range be meaningful for different definitions of meaningful. I'm going to look at unemployment data by county in the US. This is, I think, circa around 2009, so middle of the recession, or deep in the recession. And I'm using unemployment data because it's something that I think that we can all really connect with in the US. Obviously, some science has geographies. Also, we come across these types of things a lot when we use heat maps. A really common technique in science is to use a heat map with color on it. And so I'm kind of using this also as a proxy for that whole world of applying color. Same thing with scatter plots, that we put color on scatter plots a lot of the time. So we have unemployment data by county in the US, and we're doing the typical default mapping. The color range spans it's actually from 0 to the max. I didn't refresh the slide, sorry. From 0 to the max in Altair. This is the default. And there's that one yellow county and that one green one. And maybe there's a little more green here and a little more green here, and maybe some more purple here. But that's about all that jumps out at me. And if we look at the distribution of unemployment rates by county in the data set, we're actually using half of our color range from 15% to 30% for just 4.5% of our data. And maybe that's a good idea. Maybe we want to do that. But maybe we don't. We could choose a color range, so a really blunt force way of doing this is to change the min and the max to better match kind of the density of the data. And to say, you know what, everything over 15%, that's just a lot of unemployment. That's just rough, no matter how much it is. Let's color that yellow. And everything under, and everything under 2%, we'll make that the purple, and everything in between, now we're gonna double the perceptual differentiation we get more than double it, between 2% and 15% unemployment. And if we compare these, I would argue that we start seeing a lot more in that lower one. We start getting to ask more questions. But why stop there? What if we flip the color scheme? So I'm picking on Veridis a little bit today. Veridis is designed to be perceptually even. And perceptually it is. You can tell the difference between the blues and the purples. You can tell the difference between the yellows and the greens. But I don't think it's attentively even. I think you notice different things in the top chart and the bottom chart. And the only difference, same exact data, same color scheme, same type of linear mapping minus how we've dealt with the max and mins. The only difference is which direction we're going. Are we going min to max or max to min? And I think I notice different things. Different things capture my attention. We could also try a different color scheme. This is spectral. Do you notice the same things, different things, new things? Obviously, a caveat that this is not a particularly color confusion safe color map, so it won't work for some of your audience. But perhaps diverging actually makes more sense for this data set, comparing to the median value, because we kind of want to know what counties are worse than median, what counties are better than median, where are we doing better or worse? So in this case, we put white in the middle at the median, purple on one end, and dark orange on the other. And I think you notice different things here, too. Just a quick note that this creates very dark extreme ends that start to look similar. We could clamp to a mid-dark max just to prevent this and kind of flood everything above and below where I've set the endpoints. I'm also using a log scale here for this one. But why should the middle be 8.5%, the median? Maybe it makes more sense to use kind of what the economists think is the ideal unemployment rate for a healthy economy of 5.5%, which we see in the chart below. And yeah, there's a lot of that chart that's dark orange, but there's a lot of that country that was really having a hard time. And yet, in the areas that are actually where there are not enough jobs for the people, we see kind of in the upper Midwest here, and can ask different questions about that. We could put in a hard cutoff to highlight areas with greater than 10% unemployment, or a hard cutoff at negative 6%, or at 6%. Different mappings ask different questions of our data. The right color mapping depends on what question you want to ask your data. The same way that the right parameters and algorithms in ML and stats depends on what you want to ask your data. And my main goal here is just be intentional, choose something. Lastly, many of our color maps are critiqued for not being quantitatively even. And I want to say that if that's what's really most important in your data set, maybe you shouldn't be using color as your major feature for mapping it, because color doesn't convey quantitative information that well. It's very qualitative. So you can try a chart that relies on position rather than color. Obviously, then you have the problem of, well, where is that stuff happening if spatial organization matters, like a map or a heat map? If you use an interactive, something that gives you interactivity like Altair or Plotly or others, you can then kind of get the best of both worlds, where you can look at things in a really quantitative space and then interact and see where those things are happening on the map as well. A few resources, CM Ocean Color Scales and SciVis Color, can help with this and be inspirational. We can also use a highlight color to focus attention. Like we saw in this example, we can use that for scatter plots, for example. Looking at all different types of movies in the background, every single point is on every single one of these graphs, but we highlight different types of movies in different graphs. We can kind of see that the dramas are all up here, and there aren't that many of them, versus the horror movies that have a lot down here. We can also use interactivity with highlighting as a really powerful combination because you can save some space, but also be able to really get at kind of those details. And we can combine this also, now we can highlight on a small multiple, see our histogram update, and get that highlighting. Each one of the bottom ones only shows that type of movie, and you can see how the highlighted region relates to the density of the entire region. And scatter plots are just so important in science, so I think this technique's gonna be really valuable for not just movies. The last thing I want to talk about is optimizing for your time, energy, and attention. I'm gonna keep this section really brief, but I really wanna make sure I mention it, because we often have data processing pipelines, processes that you run regularly for similar types of data. And this is a really fantastic place to really invest in making choices about your visualization, because if you make the choice once, you get to reap the benefits over and over and over again. We often want to know first, kind of, is the data okay? Is it broken? Did my sensors work? Did my microscope work? Did my cells all die? And is there anything interesting here? Is there something that I should dig into more? Did I make a discovery? And in these situations, I say that we should create many charts, mostly boring. Important stuff is obvious. And I think mostly boring, I sometimes feel like sometimes you feel guilty of like, oh man, there was nothing in that chart. But if there was nothing in that chart, it meant that your data isn't broken. That is great. And this is a quick case study. This is a collaboration with Google Accelerated Science and Caltech. We're combining 3 different things, A, B, and C, and looking for areas of interest, local min, max, and slope changes. I realize I'm being pretty vague. But we took this chart, which was like not a bad chart, but we had some issues with it. Our max values were more eye-catching than our mins. It was really hard to see interesting in the mid-color scale. And if we had an extreme value that was twice as large as everything else, it would just completely wash out the color scale. And often our super extreme values, especially on the max side, just were not reliable. They were more likely to have a problem in them. So instead, we switched to small multiples. So instead of 1 triangle, we now look at 5 triangles. We have an intentional color. We also have a fallback for color confusion, so we have a different color map we can use for people that need that. And we optimize for seeing something important quickly. So these each have a different mapping. We have high to low, low to high, just within the first standard deviation, median to min, and max to median. So in summary, before I get kicked off, is it good or bad depends on your goals, context, and constraints. Please create small multiples, many related charts, use color intentionally, optimize your charts for your time, energy, attention. And if you're a tool builder, I would love to have this be easier. Thank you very much. And thank you to all of us.
Thanks so much. That was really interesting. Oh, I don't think the mic is on. Oh, here we go. Great. So we have some time for questions, and I'll try and bring the mic around since the room's really crowded. Try not to crush anyone. Do we have any questions?
Hi, thanks for the excellent talk, especially for the humor and the content. It was great. I wanted to know, since you're speaking to the tooling community or developers, what are some of the tools that you would love to see? There's dev sprints on Saturday. If there's something that you could ask for the immediate attention for.
Am I going to get booted out of the room if I ask for ggplot in Python? And I think actually the second one would be making, on a more specific, is making it easier to manage color domains explicitly, and color domains and ranges. And secondly, making it easier to facet by different visual elements, not just by different categories. And I should say, I really appreciate all the tool builders. I use a lot of tools, and I appreciate all the work that everybody's doing to make my life easier.
So this is a question more from the extreme value problem that you were showing. Sort of one solution which people often go towards is just take the log of the actual values and then plot it. I'm just trying to see what your opinion on those is. Is that don't go towards those techniques because then there's also the explanation portion, and then it's not explainable to everyone, or it's just that you're more you prefer design techniques more which target that problem. So.
I think that's a great question. So the question, about going to log. I think log makes sense, is great when the data is kind of inherently in a log form. But if you're just trying to deal with the fact that sometimes every once in a while your data usually ranges from 0 to 0.2, and every once in a while you get a 0.4 because there was dust on your microscope, then I'd rather deal with that more explicitly if most of the data actually is in a linear range. So I think, and actually I didn't talk about it today, but in my own work, I often do things where maybe I'll set the color breakpoints based on the density of the data. So I'll set them at specific percentiles. So I'll intentionally make something that is not perceptually even to be able to hopefully see differences where the differences are most important in the densest regions of the data. Thanks.
Hi. Thanks so much for the great talk. I agree with everything that you said. As a follow-on, all day is in front of a computer for most of us, and so visual fatigue is pretty common. What are your suggestions or your takes on what is optimal amount? Because you really can go overboard with hundreds of plots. But as you said, having small multiples of a similar plot is always really useful. How do you balance that?
Really large computer screens.
I have 4, so yes.
No, I think that's a real question. I definitely often have, just I'm scrolling through lots of charts that I've made and sort of at some point get lost of trying to remember which ones were the important ones, and kind of go through a process of like making lots and then culling and then making more and then culling it down. And I would err on the side, I think in general we still don't look at enough of our data, so I would generally err on the look at more. And if you're looking, and I think also just kind of in the place of being more intentional, I guess could also help, like really trying to think about like what about my data do I think is most important, and can I make visual choices that match that sense of importance? And using something, I saw the Plotly talk before here, I thought it was really cool how they're lowering the bar to changing visual aspects of your data. So I think playing with those things and trying to find a good space and trying to, based on what you think is important or what you're discovering is important, that can hopefully help narrow your design space a little bit, but make more charts.
So in recommending to use the color, what would you suggest to avoid bias by the analyst in creating colors and pushing the viewers to some direction that the data may not be suggesting?
I come more from the place that our data is always biased to begin with, and I think that, I very much believe in it's really important to be honest to the data, but I think that can mean, I think people often take that as like, oh, do the default thing, but the default thing is often not actually the most honest to what's in the data. So I think go with integrity and do your best. I think that's where peer review comes in, working with colleagues, trying different things. And there's actually some things around, like if you try 8 different color schemes or different color mappings and you only notice it in one of them, is that because you didn't notice it in the other ones, or is that because it's not there as much? And do more analysis with other techniques and follow up with stats and do science.
Cool. That was really, really great. Thanks so much.
Thank you all so much.